when talking. So of course I want to thank the organizers and thank them for giving me the opportunity to speak to you today and get you through that pre-lunch lull. Hopefully it won't be too painful. Back in 2019, I was a fresh-faced postdoc at McMaster University, or fresh-faced as I've ever been, anyway. And I was awarded an ALMA Large program. I was very lucky. And once we got over that initial excitement, we started taking data and we realized we were running into some challenges. So we had a large collaboration spread over different institutions, different countries. We had a ton of data coming in all at once. And we had fairly complex, data processing and data analysis pipelines. And we were struggling to wrestle with all these different challenges. And I think, I'm not unique in that. These are very common problems that are cropping up, particularly in modern radio astronomy research. And basically, science platforms saved our bacon, really. We were able to overcome them. So this is what I want to give you today, is a user's perspective on science platforms. In terms of these problems that I faced, well, you can actually show that they're common across astronomy just by digging into some of the numbers. So we have on the left here the number of IAU national members as a function of time, which essentially this is like countries that are members of the IAU in which professional astronomy is ongoing. And you can see that almost 90 countries are members of the IAU. That's half the countries in the world, give or take, have some sort of professional astronomy going on within them. Then if you go to ADS and you look at, okay, what's the size of the author list for papers that mention, some of the common radio arrays over the last 20 years, you see that the average number of authors has doubled in that time. We've gone from 5 to 10. So astronomy has globalized and collaborations are growing all the time. We also have a complex set of astronomical software. All of us probably have used AstroPy at some time. Well, AstroPy's code base is about 800,000 lines of code, which is comparable actually to 2 space shuttles or 14 times War and Peace. So this is a serious amount of complexity within our codes, and you can do this exact same plot. It's very similar actually for CASA and other astronomical codes. It's not just the size of the code base, it's the dependencies. So here we have what's called the dependency map. It's for the software that images the black hole for the EHT, okay? And you can see it's a big web of complex version-specific dependencies. And this is as simple as it gets for this software. And so we have, again, this problem of big code bases, lots of dependencies. Managing this is a non-trivial task. Finally, it's become cliche to say that radio astronomy data is big, but we all know this, we agree this. Of course it is. We have Russ Taylor's plot from 2020 plotting the various radio arrays going into the 2030s and the data volumes for each array. And you see that SKA sits right at the top of the tree there. It's so big, I don't even know what number, how you say that number at the top. It's 100 million terabytes, whatever that is, peta or yotta. Something like this. And then on the right-hand side, I really want to make the point that yes, radio astronomy data are big, but they're not big all the time for the user. In fact, what you have is varying demand. So if you're dealing with data cubes and huge surveys, of course, you're up there with big resource requirements. But if you then collapse that down into your map or your spectra, perhaps you're not processing anymore, your demand goes up and down, it fluctuates. And so it follows this blue curve here. And if you just provide a static resource provision for some team to do their data analysis or their processing, what you end up with is either of these 2 scenarios. Either you over-provide, and in which case you're inefficient almost all of the time, or you under-provide, and in which case you don't meet the use requirements, or supply does not meet demand when it comes to computing. And this final point here is really why I want to stress that we can't just tackle this as scientists with HPC clusters at universities. We have to move away from that model where, you know, a group or a faculty member buys a cluster and does their group's processing on that cluster, because they're extremely inelastic. You know, you have to actually have physically the space and also the money to expand a compute cluster. They are extremely expensive as well. So at the cheapest end, they're tens of thousands of dollars, and they run into hundreds of thousands or even millions of dollars per group, per cluster. And because they sit behind often firewalls at universities and so on, they're very, very impractical for large collaborations. Sharing data, getting authorization and access for members that are outside of your organization is very difficult. And I would say also that when you take these three problems together, you inbuild an equity issue into your science straight away. So what you have here is that only the most well-resourced groups and communities can efficiently tackle their science because of these issues. So this is where science platforms come in. So I'm going to be talking about the CANFAR science platform because it's the one I'm involved with, it's the one I know, but it's but we are not the only game in town. There are many other science platforms available, as they would say on the BBC. And you can, you can take a lot of what I'm saying as just being in support of this mode of working in science platforms in general. So here is a schematic of what a science platform looks like to the user, or the CANFAR science platform looks like to the user. You have your groups or your collaborations down at the bottom. They go to a web page, they log in. And then what's served to them is customizable compute environments that can have preloaded software. It can have their own software already ready to go. You can mount data sets to the back end so that, you know, the platform is next to the data and you don't have to transfer in and out. And critically, you can deploy on cloud computing resources wherever they may be, and that allows you to scale up and down. And there are plenty of, you know, off-the-shelf software that allow you to manage this. And of course, you can plug into third-party tools, you know, Binder, GitHub, we have Carter installed, and so on. So what does that look like in practicality for someone like me doing radio astronomy research? Well, here is just like 4 screenshots, and I struggled with kind of how to show this, but I think this gets the point across sufficiently well. We have a web page at the top left where you can just go, you log in, your team can log in, and the permissions are shared and managed by the group themselves. And then depending on your workflow, you pick the computing environment you want. It really doesn't matter, it's super flexible. So we can, I like to work in Jupyter Lab, so this is the top right, is a standard workflow. Select your Jupyter Lab, select your resources, and away you go. We have a desktop environment that you can just fire up, and this is great for things like legacy versions of CASA and so on that require a desktop for a lot of the visualization tools. And then, of course, we have fantastic tools developed by others like Carter and so on that is used for visualization. Now, these are just off the shelf provided as part of the CANFAR Science platform. But the one thing I really want to make clear, and something I think CANFAR does particularly well, is it allows user-contributed software via software containers. For those of you that don't know, a software container is just a way of packaging up software so you can deploy it wherever you want. And so as a user, I can say, I want to run on this operating system, I want this pipeline, I want this software pre-installed for me and my team. I write a very simple Docker script that's taken, you pop it in a repository, and it can deploy very quickly onto whatever resources you want. And what it basically enables the platform to serve everybody's needs, because we're not forcing our way of working on you. We just allow you to dictate what compute environment you want. And then the final point with this slide is that if you're a power user or a group that just is going to hog all the resources, you're going to need a ton of compute power, say, a lot of CPUs. Well, it's very easy, as long as you have those resources, to just plug them into the platform at the back end here. So to your group and your users, it's transparent. But when they go and they log in, it just deploys where you want them to and deploys onto your resources. So this is also possible, and I think it's this flexibility that really makes CANFAR and the model in which CANFAR is trying to push stand out. Okay, so just very quickly what this looks like to the user. Again, you go to the same web page, you log in, and here we have 3 examples where users decided they wanted to contribute their own software. We have an exposure time calculator for the Castor Space Telescope. We have at the bottom left a co-op student of mine liked working in VS Code, so we have VS Code on there, and he put this together. And then we have another student likes coding in Julia. So this is a Julia scripting environment that I know nothing about. So it's hyper flexible. All right, so I've talked about what it can do, and now I'm just going to briefly mention what we want it to do in the future. So basically, federation is the future, I think. And what do I mean by that? So cloud federation. If you go to the dictionary and you look up this word federation, it is an encompassing entity formed by uniting smaller, more localized entities. So why am I telling you about this? Well, particularly with the SKA, but these big radio arrays, it allows these platforms to serve their global community. So you would have, for example, the same entry point portal into the platform, but depending on where the user is, what group they're a part of, where their data is, their resource allocation is deployed in a different place. So this is really, there should be a map under there as well, never mind. But yeah, imagine if there were a map of the world underneath this diagram. So you can have, the platform served next to the archive exactly where the data is, so you minimize data transfer. You could have one version of the platform deployed. Hey, it appeared, there you go. You could have another version of the platform deployed at the data processing centers or in China versus Chile or so on. So it allows a single service to be provided to an entire global community. Okay, so I'm just going to pop up my conclusions here. Well, it's not really conclusions, it's more, these are what I see as significant barriers to us doing science as we enter this new age of huge radio arrays. We have large dispersed teams, we have very complex software base, and we have obviously this big data challenge. Thank you. Yeah, and science platforms help to reduce these barriers, and I think will help us as a community push forward and overcome them. And my final point is, if you're interested in either this or anything else that the CADC and CANFAR do, please go and see the CADC booth at the poster session later today. I believe that if you're lucky, there's free booze and or free t-shirts, I'm told. Enjoy.
Great talk. Questions? Ziggy. Hand up so she can see you.
Thanks, Toby. That was great. I've been using CANFAR with the China Free collaboration. It's been really great, and I really enjoy using it. I was wondering how scalable is this, or how easy it is to transfer this to other countries or data centers. Do you have any feeling for that?
We have some feeling for it. So we've done a test to see if we can deploy onto other cloud architecture. So right now it's Compute Canada. So we deployed on Google Cloud, I think, on like a free allocation, and we were successful in getting it to run. It takes work though, so it's non-trivial amount of work to build in this kind of multi-cloud model. But the technology exists. So the challenge is not really technical, it's like a combination of financial and political, really.
Yeah, thank you.
Behind you? Is it?
Thanks for this great talk, Toby.
Sorry, there you are.
Over here. I'm just wondering if you could say something about whether there are tutorials or training opportunities for teaching users how to best use this platform.
Yes, so there is GitHub, there is documentation on GitHub. Helen Kirk at NRC has done a ton of work putting together tutorials and documentation. Like any community, it's always best if it's kind of user-driven as well. So we encourage people, it's all open source, encourage people to file issues so people can use that as a resource and contribute, their own use cases and examples. Because part of the thing when you build in this flexibility is that there is an almost infinite number of use cases. And so we can't provide documentation for every single one of those.
Joe,
yeah, awesome talk, Toby. You really put a lot of stuff in concept for me here. I was just thinking about the current funding model for this kind of stuff, right? Like I write now personal grants and I ask for a cluster. Is there a template we can develop for this to say like that can implement, plug it in instead of me having to go to my local ICT in my department and go, okay, I want a cluster of X amount of money. Is there a way we can make this more common across countries? I'm thinking now SRC, SKA stuff. Is this something discussed in the community to say like, I want to bulk in this, I've got, here's 250,000?
This is an excellent question, and it's sort of the reason I'm talking in the room, and I'm not the decision maker you need to be speaking to here. But in my ideal model, this is served by the observatories to their user community. So if I want to process ALMA data, SKA data, this is at no cost to me. It's like the NHS, free at the point of use. And then if organizations such as those or government labs or whoever want to include resources for this in their request to their, say, national cloud providers and so on, then I think this is the way to go. But it shouldn't, I don't understand why we put the onus to deal with the data on the user. It should be provided for that, and it's the observatories and the bigger organizations that should pick up that tab, I think.
Okay, online question.
Yeah, this is a question from Ilse van Bemmel. How do you handle user authorization currently?
That's probably a bit too technical for me because I'm not a developer. So CANFAR provides lots of different services like storage and management and so on. And we have just a single sign-on service. So when you log in, you're logged into the CANFAR system and you can access the platform or your storage allocation or whatever. Something that's really nice is that we have user-managed groups. So I have a big collaboration and they all sign up and get a CANFAR account, and then I can add them to my collaborations group, and then suddenly the resources that contain the data, the repositories and the file systems that contain the data and the scripts and so on are available to any of those users. So the key here is in the group, authentication, let's say.
One more question at the back there, and that'll be it.
Hi, thank you. That was really interesting. How does this compare, and have you spoken with the particle physics community in Europe? I know they have a large iris network of compute and software, and I find it frustrating.
Is this SWAN, or you're talking about CERN? They have SWAN or something like this.
So the one I'm talking about is called Iris.
I don't know this.
We'll talk afterwards. But yeah, I think this sort of software system could be built on top of their hardware and would make it potentially much more user-friendly.
Right, okay, yeah. I mean, this is very much still in development, and the nice thing about doing it in this way is that you can plug in, either improved hardware, or you can add in functionality to the platform at a later date. It's a very flexible architecture choice, basically.
Cool, thank you.
Okay, could you please thank Toby and all this morning's speakers again.